Hello, my name is Dylan Radulski, and this is Lab 4, Magnetic Braking with Faraday, Physics 2212, Georgia Tech summer semester. The purpose of this lab was to collect data on a fog magnet through an aluminum tube and connect it to Faraday's law. The system was the aluminum tube and the magnet, the surroundings was everything else. The results for the experiment was an experimental time average of 1.12 seconds and a computational time average of 0.719 seconds. Some fundamental physical concepts used were Faraday's law, the Biot-Savart law, and Newton's second and third laws. The procedure. Use a magnetometer on a phone to determine the north pole of a magnet, and then use a stopwatch while the magnet falls through the aluminum tube. Repeat this process 5 times and make sure to stop the timer as close as possible to the magnet reaching the bottom. Here was some observational data that I used in the code to make sure my readings were as close as I could to the truth. The aluminum tube length was 0.3 meters, the width was 0.005 meters, the inner and outer radius respectively was 0.025 meters and 0.03 meters, the magnetic mass was 0.025 kilograms, and the average time it took was 1.12 seconds. And then from lab 2, I had the same magnet. The mu of the magnet was 4.18266 amperes meter squared. Here is the code shown below. Here is some of the geometry of the tube, the information I had to put in there. Here is the properties of the magnet, and here's the loops and everything that gave me the results. Here's the model results. This is the image of the magnet post having fallen. This is velocity. You can see it initially starts going very fast, but then Faraday's law kicks in, and you can see that it slows down almost entirely. The acceleration slows down almost entirely, and it only falls at a constant rate until it reaches the bottom. And it does this in a recorded 0.719 seconds. Some possible sources of error could have been me measuring the tube or the magnet improperly, which would give improper readings in the code and would end up having the magnet fall faster than what happened in real life. My timing might have been slightly off, and any rounding errors in the math, as well as if the magnet hits the side of the walls of the tube in real life, that will slow it down on top of Faraday's law. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Due to Ohm's law, decreasing the resistance would increase the induced current. The magnetic field would be stronger, and this would slow the magnet faster. What if holes or slots were cut out into the tube? How would this affect the ring currents in your model? Less rings mean less currents, means weaker opposing magnet fields, so the magnet would fall much faster. And back on this one, since assuming that by as close as possible to 0, it means infinitely close to 0, that would mean the magnet would essentially stop or fall at an insanely slow speed where it seemed like it was almost floating in space.